Hey guys, so this is the third video of lesson 1. In the last lesson we looked at what happened with current in a series circuit. We said that current is the same through each resistor or throughout a series circuit. So along this line of the series circuit, anywhere where I'm coloring in red, current will be the same. Whereas for a parallel circuit, wherever I'm drawing in red, the current will be the same. But the components that I'm going to do in a different color, so what I'm doing in blue and what I'm going to do in green, the blue plus the green added together will give you the red. So maybe it's a little good idea to highlight that. So what I'm saying is the current going through A2 plus the current that's going through ammeter A1 will equal the current that's going through ammeter just A. Okay, so that's current in series and parallel circuits. Then we had a look at potential difference, and I said that the potential difference across this light bulb, sorry, it's not a light bulb, the potential difference across resistor X plus the potential difference across resistor Y, those two added together will be the same as the potential difference across both of them. So if I had a voltmeter and I connected it across both resistor X and Y, what I'm saying is that the green is equal to the red plus the blue. So resistor V, voltmeter V would have the same reading as voltmeter 1 and 2 added together. So we can say V is equal to V1 plus V2. And that's for a series circuit. So to summarize, potential difference is shared, or you can even say potential difference is divided. If you want to write divided rather than shared, potential difference is divided. Actually, let's write this together, guys. So I want you to write this in your notes, please. Potential difference is split or divided by each component, across each component, across each component in a series circuit. What I've written in blue basically means what they've got there, but it also includes other components. So if I had light bulbs, it's not just resistors that can be in series, you can have other components like a light bulb. So my definition is a bit more broad. All right, let's look at a parallel circuit. What we're saying there is that the potential difference along any part of this blue wire is the same. And because it is actually the same piece of wire. So if I connected a voltmeter on the left-hand side, so maybe I do this in green. So if I connected the one side of a voltmeter, it would have to be the positive side of a voltmeter because this is the positive terminal of the cell, of the battery. And I connected the other end to the negative side, to what I've done in blue on the right-hand side, the potential difference would be the same anywhere along that point. Okay, so I could even have, let's put in an extra random voltmeter. If I put a voltmeter there, they would all read the same. I'd like you to please add in a voltmeter here. And we can even give the numbers 1, 2, can call this 3 and 4. So reading on voltmeter 1 is equal to the reading on voltmeter 2, which is equal to the reading on voltmeter 3, which is equal to the reading on voltmeter 4. So the potential difference is the same across each resistor or each component in a parallel circuit. Okay. We will later do combination circuits where, say for example, I put in a light bulb over here. So if I took this out, so later we're going to have a look at what would happen if you had a light bulb in your circuit as well. If I connected a voltmeter over here and I called that voltmeter 5, then I could say that voltmeter 5 plus voltmeter 1 and 2 would be equal to voltmeter 4. So I'm going to add them up together, voltmeter 1 and 2. And remember, voltmeter 1 and 2 is the same as voltmeter 3. So I could even say voltmeter 5 plus voltmeter 3, because 3 is actually the same as 1 and 2. That's equal to voltmeter 4. And we call that a combination circuit where you've got a parallel part and a series part. Okay. Now let's look at what happens when light bulbs blow, when you've got more than one light bulb in a series in a parallel circuit. So in a series circuit, if one light bulb blows, the other will stop working, and the reason why is current cannot go from the negative terminal of the cell through the bulb and back to the positive terminal. So please don't ever think that the one light bulb will be on and the one will be off. Because no current flows, your circuit is broken, and in a broken circuit, no current flows. So again, do not think that current will leave the negative terminal of the cell, go through the first bulb, so the first bulb will be on, and that's where it stops. No bulbs will be on. So if this bulb blows, let's do it in red, that one's blown. If that bulb is blown, neither bulb will work. Okay. However, in a parallel circuit, let's say that there was a bulb, this one on the top here, and it blows. Is there still a path for current to go from the negative terminal of the cell through another light bulb and back to the positive terminal of the cell? Yes, there is. So what we're saying is that this bulb is happy, it's on. Smiley face means on and happy and bright. Sad face means off. So over here, this one is off. This one is blown. But even though the bulb on the right is not blown, it's still off, it's not working. Over here, this bulb is blown, but this bulb is on. Okay. So in a series circuit, when one bulb blows, the other bulb would not be able to light up. In a parallel circuit, when one bulb has blown, the other bulb will still light up, and that's because there's more than one path for current to take. Because there was more than one, now there is only one, but at least there is still a path for current to take. So there is still a path, or a closed loop if you want to say that, for current to move. Through the circuit. Okay, so in a series circuit, if one component fails and there was only one path for current to take, this was the one path. If that path gets broken, then no current will flow. So both bulbs will be off. In a parallel circuit, if one bulb's blown, there's still another path for current to take, and so the bulb in that path will light up because there is still a path for the current to move through the circuit. Let's look what happens if you've got a series circuit and you add more and more bulbs. So if I had just one bulb, so let me change this slightly and show you what it would look like. Unfortunately, I can't show you the FET simulator right now on this iPad, but you can do it yourself if you want to. You can build a circuit in FET simulator, have one bulb in it, and then add a second bulb and see what happens to the brightness of the bulb. Remember, brightness of the bulb is represented by the length of the lines, the yellow lines coming out of the bulb. So say, for example, this circuit looks like this. So that bulb is gone. All right, so there's a circuit with just one bulb in it. That bulb would be very bright. So I would make that a smiley face because it's quite bright. All right. But if I added a second bulb and I added it in series, so there we go, we've got a second bulb. Both bulbs would be on, but it would be slightly dimmer. Okay. So they'd still be there, but it will be slightly dimmer. And the reason why is because there'd be less voltage across each bulb. Remember, if I connected a voltmeter here across the cell, let's say that that was 10 volts. If the light bulbs are identical, it would mean that each one would only get 5 volts and 5 volts. Whereas previously, when you only had one bulb, say for example I had another circuit with just one light bulb in it. If that was a 10 volt battery, so if we had a voltmeter across that battery and it had a reading of 10 volts, and I put a voltmeter across that bulb, and that would mean that this voltmeter would also have 10 volts, then all of the 10 volts from the cell or from the battery is going to that bulb. Whereas if I've got two light bulbs, each one would only get 5 volts. So if I put a voltmeter there, it would be 5 volts, and if I put a voltmeter here, it would only have a reading of 5 volts. So each bulb has only got a potential difference across it of 5 volts, and so it would be a bit dimmer. Okay, let's have a look at what happens in a parallel circuit. Still, sorry, on the series circuit, another explanation, another reason why it would be, the bulbs would be dimmer when you add more and more. Remember, light bulbs are resistors. So let's just say that this bulb had a resistance of 1 ohm, and that one had a resistance of 1 ohm, and this one has a resistance of 1 ohm. In this circuit, there's only one bulb, and so the resistance is only 1 ohm. So the current isn't slowed down as much as in this circuit, when we've now got 2 bulbs with 1 ohm and 1 ohm. So the total resistance for this circuit with 2 bulbs would be equal to 2 ohms. More resistance, remember, as resistance increases, current would go down. If you had resistance decreasing, then current would go up. Please remember that there's an inverse proportion between resistance and current. Okay. In a parallel circuit, remember we've got 2 paths for the current to take. So all of the current's going to go along the blue. So anywhere along that blue line, the current would be the same. But it's going to split, and some's going to go along the green line, and some's going to go along the red line. Okay. And because there's more than 2 paths for current to take, more current will be able to flow through the circuit. If you want to think of it as if you were standing by the printing office and you needed to get from there around the hall to my classroom, and there was only one route for you to take, it would be quite slow. Say there's a lot of grade 7s in your way. It would be quite slow for you to take that path. Whereas if some of you went around the hall and some went outside the tuck shop area, then there's 2 paths for you to take. So more of you could get from the printing office to my classroom in less time. So more current can go through. So what I'm saying is, let's say that there was 1 amp of current going through the blue part of the circuit, 1 amp and 1 amp. And if the light bulbs were the same, we'd have half an amp going through there and half an amp going through there. Okay, and if that was the case, because there's two branches for the current to go, it can move through more quickly. So if I'm adding more and more resistors in parallel, there's more and more branches for the current to take, and so it will move faster. So there's one path, there's another path, 2 paths, current can move faster. So if you're adding resistors in a parallel circuit, let's actually make a little note on the side here. Okay. Adding resistors. Let's talk about a series circuit first. Okay, so adding resistors in a series circuit increases resistance. If you increase resistance, decreases current. And if you decrease the current, that will mean that you'll have dimmer bulbs. Okay, let's talk about a parallel circuit. Adding resistors, even though they're resistors, they still create another path for current to go if you add them in parallel. So adding resistors in a parallel circuit decreases resistance. Adding resistors in a parallel circuit decreases resistance. And remember, if you decrease resistance, you're going to increase current. Increase in current will lead to brighter bulbs. And I just want to talk again about the reason why adding resistors in a circuit decreases resistance. Sorry guys, I'm trying to get yellow. Okay, adding resistors in a parallel circuit decreases resistance because there are more than one path for the current to take if you're adding more and more resistors in parallel. If I said to you what would happen in a circuit if we had a third bulb connected in parallel? Okay, that would mean that there's now 3 branches for the current to take: the top green one, the middle red one, and the bottom black one. So if we've got 3 paths for the current to take, more current will flow because there's less resistance. Because there's 3 paths, if you've got more current, the bulbs are going to be even brighter. So if you had 3 resistors, they'd be super happy, super bright bulbs. All right. So in a parallel circuit, brighter bulbs when you adding resistors in parallel. Remember, bulbs are resistors. Adding resistors in parallel will give you brighter bulbs, whereas adding resistors or bulbs, because bulbs are resistors, in series will give you dimmer bulbs, because resistance goes up, current goes down. Whereas in parallel circuit, adding resistors in parallel, you've got more paths. More paths means less resistance means more current means brighter bulbs. Okay, I showed you here how you would have 10 volts from your battery, and potential difference gets split across each component of a series circuit. So the one component would get 5 volts, the other component would get 5 volts. Remember, the 5 plus 5 adds up to give you 10. And in this circuit, if this was a voltmeter here with a reading of 10 volts, I want to know, can I get from that voltmeter to, if I connected a voltmeter here, let's call that voltmeter 3. I'll put another one here and call that voltmeter 2. And I'll put another voltmeter over here and call that voltmeter 1. If I ask you, can I get from voltmeter 1 to voltmeter 2, what would you say? Let's trace. Okay, so I'm going to start here at voltmeter 1, and I can get from voltmeter 1 to voltmeter 2 on the negative side, and I can get from voltmeter 1 to voltmeter 2 on the positive side without crossing over any component. Going along these 2 yellow lines that I've just highlighted now, I haven't crossed over any battery or resistor or cell, anything like that. I haven't crossed over, so they'll actually give you the same reading. So we can say that voltmeter 1 would equal to voltmeter 2. Now I want to know, can I get from voltmeter 3 to voltmeter 2 and voltmeter 1? Let's have a look. On the positive side, I can get to voltmeter 2. On the negative side, can I get from voltmeter 3 to voltmeter 2 without crossing over any component? Yes, I can. So we can then say that voltmeter 3 is equal to voltmeter 2. And let's see, can I get from voltmeter 3 to voltmeter 1? I'll have to do that in a different color. Let's do it in orange. So from voltmeter 3 on this side, can I get to voltmeter 1 without crossing over any component? Yes. Can I get from this side to voltmeter 1 without crossing over any component? Yes. So what I'm saying then is voltmeter 1 is equal to voltmeter 3. So all of them are actually equal to each other. Voltmeter 1 is equal to voltmeter 2, which is equal to voltmeter 3. So the point of showing you all of this is that if this potential difference was 10 volts, the potential difference that this bulb is getting is 10 volts, and the potential difference that that bulb is getting is 10 volts, because potential difference in a parallel circuit is the same. Okay, so because potential difference in a parallel circuit is the same, each one has got more potential energy going to it, and so you're going to have brighter bulbs in parallel than in series, where, remember, potential difference was split. We had 5 and 5, whereas here we've got 10 volts and 10 volts. Okay, so again, if this is 10 volts across your cell, that's 10 volts, and this one would read 10 volts, and voltmeter 1 would also read 10 volts. So we've got 10 volts, 10 volts, and 10 volts, compared to the series circuit where you had 10 volts across your cell, whereas each light bulb only got 5 and 5, and that's why bulbs in series are dimmer, bulbs in parallel are slightly brighter. Okay, so bulb brighter in parallel because we've got higher voltage across each bulb and more current. The reason why I've got more current, remember, due to less resistance. Due to less resistance. Okay. This is just showing us that the current going in on a series circuit, current before a resistor is equal to the current after a resistor, so I1 is equal to I2, I1 equals to I2, and it's equal to the current going out of resistor 2, which is I3. So it's just showing you that current at any point in a series circuit is the same. Remember in the video that I showed you last when we did it on the FET circuit, the online circuit, and I moved the ammeter around, current at any point in a series circuit is the same. If I connected a voltmeter across R1 and I called it V1, and I connected another voltmeter across R2 and I called that V2, and I connected a voltmeter across R3 and I called that voltmeter 3, and I had one voltmeter across all of them and I called it voltmeter 4, which is what they're showing you over here. All that they're saying is voltmeter 1 plus voltmeter 2 plus voltmeter 3 would equal to voltmeter 4. So over here, if you wanted to call this one, if you want to call this voltmeter 4, that's fine. So voltmeter 4 is equal to voltmeter 1 plus voltmeter 2 plus voltmeter 3. Okay, and if you wanted to get resistance, you'd have to add up the resistance of resistor 1 plus resistor 2 plus resistor 3, and that would give you the total resistance in a series circuit. So in a series circuit, add up all the resistors to give you total resistance. If you want, you can call this R total. So total resistance, you add up all the resistors in a series circuit. Okay, let's talk parallel circuits now. So current going into parallel circuit, if we represent that in red here, current going in is going to split. Some's going to go straight through resistor 2, some will go to the right through resistor 3, and some is going to go to the left through resistor 1. So if you add up the current going through resistor 1 plus the current going through resistor 2 plus the current going through resistor 3, if you add up all of those three, you're going to get the total current. If you want to call that I with a little baby t below it, subscript t, you can do that. So total current is equal to current going through resistor 1 plus current going through resistor 2 plus current going through resistor 3 in a parallel circuit. There's a mistake here for potential difference. Remember, the symbol for potential difference is a V. Symbol for current is an I and resistance is an R. So this, guys, please make this be V is equal to V1 plus V2 plus V3. And what we're saying is this: if I were to connect a voltmeter across resistor 1, if I had a voltmeter and connected it across resistor 1, and another voltmeter and connected it across resistor 2, and a third voltmeter connected across resistor 3, if I added up the potential difference in each of these 3 voltmeters, it would equal to the total potential difference. So I could have another voltmeter here, if I call that voltmeter 4, and I could say that voltmeter 4 is equal to voltmeter 1 plus voltmeter 2 plus voltmeter 3. Build a circuit like this on the FET simulator and you can see if you want to. This equation is how we calculate resistance in parallel, and that explains why resistance decreases when you add more components in parallel, but we're going to look at that in a later lesson, so don't worry about this for now. Leave that equation for now. Okay, I want you guys to draw circuit diagrams for these circuits. I'm sure you remember from last year. These are the types of diagrams that you do last year. Remember, pencil and ruler, please, guys, otherwise you will lose marks in tests and exams. It has to be pencil and ruler. So notice over here, we've got a cell. This is the negative side. This is the positive side. So when I draw the cell in circuit symbol form, the long side is positive and the short fat side is negative. You don't need to show the plus and minus signs, but it's a good idea to to think it when you're drawing it. Okay, so again, please use a pencil and a ruler. That's the circuit diagram for the circuit. Over here, we've got a switch. It's closed, and the reason why I know it's closed, well, we can see it's closed in the picture, but also there's these lines coming out of the light bulb to show that the bulb is on. So we're going to add in a closed switch. Okay, I would like you to please complete this. So pause the video and then complete it, and then I'll show you what it looks like when in the memo. So please pause the video and start it again once you've completed up to the end of diagram F. So you've got to do diagram A, B, C, and D on page 6 and E and F on page 7, and then restart the video. Okay, this is the memo. Remember, there are different options. If you wanted to put your light bulb not over there, but you wanted to have your light bulb over there rather, that's fine too. So your diagram may look slightly different to mine, that's okay. So there's a circuit diagram for the same circuit, just with an open switch. Remember, positive side of the cell, positive side of the cell, negative side of the cell, negative side of the cell. Here's the circuit. Two cells connected in parallel. Sorry, two cells connected in series. Guys, there's the one cell, there's the other cell. There's only one path for current to take in this circuit, so those two cells are connected in series. So if I asked you to describe the circuit in words, you would say we've got two cells connected in series. There they are. Then we've got a cell, just one cell. Then a closed switch, and those are the only components we've got in that circuit. Over here, we've got a parallel circuit, so there's actually two paths for current to take. When you drew your diagram, if you wanted to do it in diamond form, that's fine, or in square form, that's okay. So if you had this rather than that, that is okay. You get to choose. So let's go from the negative terminal of the cell. Current goes through there, through the closed switch, up, and over here it's going to split. At this point, it's going to join back again and go there. So if I connected an ammeter anywhere along that blue side, I'd get the same reading. When it splits, some would go through the top bulb and some would go through the bottom bulb. So the current in the yellow plus the current in the red line would equal the current in the blue line. Okay, then for C, we've got three cells connected in series, one after the other. It's a little bit hard to see which way around.